All right, ladies and gentlemen, shut up, sit down, and enjoy the show. Actually, I don't care if you enjoy it. I already got your money. Haha. Wait, they no, they didn't pay for this. You guys didn't pay? Whose money is this? What do I? All right. So we're gonna talk about related rates. All right. Now, normally we have thought of the derivative as the slope of a tangent line to a function, or the formula for the slope of a tangent line. So this was already we all got matching tattoos. We can show your moms and they could be disappointed or not disappointed. Depends on just what your mom's stance on tattoos. The derivative, or your mom's stance on calculus, I guess. The derivative of a function can be thought of as a formula for the slope of the tangent line to that aforementioned function. So, what else? Well, in context, the derivative can also be thought of as a rate of change. We're going to add to the tattoos. Sorry, Mom. Uh, in context, it's a rate of change. Well, what the heck am I talking about? Let's see. Suppose we have a function, m, where m is in miles, and this function is in terms of h, where h is going to be hours. And this function, it would give us however many miles traveled if we input the number of hours. That's really what it's saying. So if we had this type of function and we took the derivative with respect to the hours, so dm dh, right? If we just took the derivative, ddh, right? Not x, h. Well, that would give us dmdh, right? dmdh, and that would be, well, the dh is matched. So if we had dh of 3h plus dh of 4, well, that would be, these match, these correspond with each other. So we have, what, just 3. dmdh would be 3, and then that would be 0, right? Because the derivative of a constant is 0. So the change in the miles with respect to the change in the hours is 3, otherwise known as 3 miles per hour. So the way that we're going to think of the derivative in the context of our problems is the change in this variable, the change in the miles, with respect to the change of 1 unit in the other variable, right? So it's the change of the dependent variable with respect to the independent variable. But that's a lot of words to write down that don't really make sense. Just think of the derivative as the rate of change with respect to something. So this is something you can write down. So this represents the rate of change in distance, which will be measured in miles, with respect to the time in hours. Maybe I should have written time. But the derivative is a rate. That's the biggest thing. Derivative is a rate. In this particular mini example, the derivative of that miles function is a constant rate of 3 miles per hour. Sometimes the rate is not constant, meaning you'll get a formula for the rate. So the derivative is a rate. That's a tattoo. I guess the second part of the tattoo. So if you're looking for a rate, chances are you'll have to take the derivative. All right, what do we got here? That was a lot of writing for not really too much. We didn't talk about too much. Maybe an example is called for. Holy smokes, that's a lot of words. But it's okay. This is actually a short problem. What? Yes. Water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 4 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? That's interesting. The first thing I notice is they're saying how fast, and then the radius at a rate. They're asking for rates, and they're giving us rates. Okay, that's interesting to think about. Rates. Maybe they're talking about derivatives when they say rates. And actually, they are. And in this case, it's centimeters per minutes. So it's going to be like a distance and a time. Well, the way we're going to consider, or the way that we're going to write down the rate for the radius, because it says the radius of the pool increases at a rate of 4 centimeters per minute, I'm going to write that down as a derivative. Usually you denote the radius with an r, so I'm going to say dr, I'll do it in red, that's fine, dr, well, minutes, I'm just going to say time, and then the time will be in minutes. That's what I should have done in the first place, but dr dt. This will represent the rate at which the radius is increasing, the radius of the pool. And that's dr dt. It's the rate will be a function of time. Like you plug in a certain amount of time. Sorry, the radius will be a function of time. You plug in a certain amount of time, and then the radius is a certain length. You wait more time, the radius will get longer. So that's how you do that part, the rate for the radius, and then it's asking for the rate, how fast, that's another rate. How fast is the area? Usually you denote area with an A. That's right, you're good, you got it. Alright, so maybe, well that's also, in terms of time, we're thinking about with respect to time, so how fast is the area? That will be represented by, I'm going to say capital A, because usually you denote area with the capital A. dA dt. This represents the rate at which the area is changing with respect to time. Yeah. Both of these are with respect to time. Rate at which area of pool is changing. And this is the rate at which the radius of the pool is changing. Both with respect to time. Most of the time, we're going to be doing this with respect to time, but usually it's just with respect to the independent variable. And in this case, the independent variable is just time. So, it's important to know what those mean. You don't have to write down this every single time. Maybe you should. It doesn't hurt unless it just takes too much time. But I would say, yeah, you can jot down something. Rate at which radius is increasing, rate at which area is increasing or decreasing. Something that I'll mention later on as we go through more examples is when you have a rate that's increasing, or like a quantity that's increasing, the rate will be positive. If you have a quantity that's decreasing, the rate will be negative. So that's something to think about. But in this case, they'll both be positive because the pool is getting bigger and bigger, which means the area is growing and the radius is growing. So they tell us right away, dr dt, maybe I'll do this part green, dr dt, that's equal to 4 centimeters per minute. cms per minute. Okay, that's 4. Nice. And they're asking for dA dt. They're asking for the rate at which the area is changing. So I put a little question mark. But you gotta always do the when. The when. I meant the D. What's the when? The when is at a certain time, because the rate is not always constant. The rate that we're finding is not always constant. So the rate could be increasing. The area could be getting larger and larger, faster and faster. Like the more time you wait, the faster it gets larger. Or the more time you wait, the slower it gets larger. So we have to find this rate at a specific time, or at a specific r value, which is the radius. So when, and here it is, when the radius is 5 centimeters, when r equals 5 cms. And I'll probably drop the units until the very end. You got to have the units at the end. But this is what it's asking. All right? That's very, very important to write down. So you write down the rates that you have in derivative notation, and then you write down the rate that you want in derivative notation, but also with the when part. So there we go. Now I'm ready to start my problem. This is crazy. It's almost a 10-minute video already. Maybe I'll take a screenshot and we'll start in the next video.